Welcome to the fourth lecture on natural language processing and its applications. My name is Włodzimierz Zadrożny. I work for IBM Research, and I will be discussing today mostly stuff relating to the Watson project. But before we do so, I would like to do a quick review of previously covered material. So on the first day, we discussed the Bayes theorem and machine translation. We also introduced a couple of simple applications, one measuring article impact and the other related to psychiatric diagnosis, in particular psychosis and manias. We discussed some details of the classical statistical model in which a machine translation problem is decomposed into building a language model here and machine translation model in this part. And we discussed the use of n-grams in creation of these simple applications in machine translation and in helping to answer some of the Jeopardy questions. Day 2 was about the complexities in natural language. So we discussed many very different linguistic phenomena. We tried to describe some of them using grammars, and we introduced the process of parsing as a creation of a structure, in particular the parse tree, that is assigned to a string of words. Yesterday, we continued to discuss parsing. In particular, we talked about the early parsing method, which allows us to do parsing efficiently without redoing any work. If you remember, I mean, sort of the main idea there is to keep the state and then to move the dot and reduce the number of possibilities by checking which of the grammar constructions are licensed by the next word. Well, from parsing, we would like to go to meaning. And typically, a representation of meaning involves writing something which we call a logical form. These logical forms are inspired by first-order predicate calculus, but there is no such canonical representation, and we showed many examples where the standard logical representation would break because of the way the language is used. Semantics is an active area of research, so we are still trying to invent different ways of representing knowledge about language and the meaning of language. And the mapping from a parse tree to some kind of a representation of meaning is very much an open problem. The next topic we discussed was chatbots, so elementary dialogue in which machines try to either solve certain problem. For instance, they try to create a reservation for a flight, or they try to pretend to be humans, and that was sort of the interesting part. And we noticed that such chatbots still are very primitive, and the reason for that is they can create syntactically correct sentences, but the way they express the meaning is very often it's very strange. So they do not work well except for in restricted domains. So the moral of that is that, again, another open problem in natural language processing is the problem of an open domain dialogue, that is building a dialogue system that is capable of discussing almost any topic. And finally, we started to discuss question answering in open domains, and in particular the Watson project. We introduced the architecture that at the basis has the UIMA platform. This is the collection of modules that allows us to create applications for text processing. It provides us with the transport on which different analysis can be passed from one analysis engine to another, and eventually the results of such analysis are either stored or presented to the users. We also discussed the problem of finding pronominal references, because that's what's needed in order to account for meaning in texts. So today we're gonna continue discussing open domain question answering, and in particular the Watson system. This is a very complex machinery. It uses search, it uses parsing, it uses a simplified logical forms. It has very complex scoring mechanism. So we will cover some of it, and in particular we're gonna cover the use of predicate arguments matching, so a simplified logical form. We will also discuss data preparation, okay, because any system that's supposed to answer questions about any domain needs some background knowledge about that domain. And a lot of different types of text went into the preparation of the Watson system. These included Wikipedia and some other encyclopedias, sources of lyrics, complete works of Shakespeare, various dictionaries, and some other resources which we will discuss in the course of this part of the talk. And if we have time, we will start discussing search and information retrieval with the idea that at some point we're going to discuss it in the context of the Watson project. But for that we need to introduce some basic notions and establish some intuitions. So a quick reminder, the way language analysis works in the Watson project is that we have the UMA pipeline where everything is happening. There is this common analysis structure, which is essentially a memory location, a place where all additional information is added. So we start with the question, with the query and some additional data. Then we analyze the query using a collection of Prolog rules. So there is a Java Prolog interface that allows us to do so. And then once this analysis is performed, again, the results of the analysis are translated into Java objects, and then they are used by some other modules. Similarly, when some text is retrieved, in order to find out, for instance, whether it supports a candidate answer, then similar type of analysis is performed using the same kind of interface, and again the results are put in the CAS. In some cases, we pre-compute some of this analysis, and therefore we can save ourselves the time at the runtime to do it for certain sources of knowledge. But question analysis and then some detailed analysis of passages still has to has to account for certain predicate argument relations. So we discussed the architecture for building text system, UIMA. This is an open source project sponsored by the Apache Foundation. And again, to remind you, the intuition behind it is that we have a sentence, okay, and what happens is that, say, one type of annotator, which is the parser, creates a parse structure here. So, for instance, it finds noun phrases, verb phrases, prepositional phrases, and maybe puts them all together into a parse tree. And then another annotator can find named entities and decide that these are people or organizations. And then a third annotator, so another program, can find the relations between people and organization, and the results of this analysis can be extracted and stored, for instance, in a database. We talked about the fact that there is more than one path in which the information can be sent in the Watson system. That's how parallel processing requires the creation of such possibilities. So we introduced the concept of a CAS multiplier, which is essentially a system that allows us to copy a CAS and send it to to more than one machine or more than one annotator. All right, so the architecture looks the way we see it here in the diagram. The question comes in, it's analyzed, and something happens, and then the answer is given with the confidence. So what happens? Well, what happens is a couple of things. Candidate answers are generated, and once they are generated, we are looking for supporting evidence. Okay, so we are looking for the evidence that this particular candidate is a good answer to the question. And sometimes we find it, sometimes we find multiple pieces of evidence, and these pieces of evidence are then combined, and the final score is happening somewhere here at the end. We will discuss this search component tomorrow. Today, we focus more or less on this part, that is on what to do about the evidence that we are finding. How do we connect two pieces of textual information to find out whether one is relevant for the other? We've seen this example before, okay? So we have a query, a question, okay, a clue, war movies, a controversial 1979 war film that was based on 1902 work by this author, or in May 1898, Portugal celebrated for 400th anniversary of this explorer's arrival in India. So with this kind of a clue, we will be trying to find the answer to this clue, and we will try to find a good answer, okay? So this would be a bad answer, or at least, I mean, this passage is a bad passage because Gary, who arrived in India after he celebrated his anniversary in Portugal, is really not what we mean by the, by the answer to this. It is not a correct answer to this question. On the other hand, here we have a passage which has the correct answer, but the problem is, how do we connect this passage with this one, with this question, given that really there are no words that are shared between two passages, except for the word may, which is ambiguous, okay? It may be an auxiliary, especially if this is capitalized. So we have to to make decisions, what's relevant and what's not. And then if we decide that a passage is relevant, how do we find a relation? And finally, what score do we assign to this relation? So we're going to leave the scoring, the details of scoring for later, but we will try to focus on question analysis, then deciding how a passage is relevant, and then how we can use this extracted semantic information. So we start with question analysis, all right? So question analysis, we have a clue, poets and poetry. The clue reads, he was a bank clerk in the Yukon before he published Songs of Sourdough in 1907. All right, so the question asks about someone, about a male, okay? But we know a little bit more about it, yeah? About him, yes? We know that he was a bank clerk in the Yukon, and he also published the Songs of Sourdough. So what it is that we can extract out of it? Well, the first thing is the focus, that is a reference to the answer. We are looking for, for someone, for a male, so we're looking for the he, all right? But then in addition, we are trying to extract something which we call lexical answer types. That is, these are the descriptors of the entity that we are interested in, okay? So these descriptors here are he, clerk, and poet, but they also include a bank clerk, okay? And that would also include bank clerk in the Yukon if we decide that we allow, long lexical answer type. In principle, there is no restriction on how big they can be and how detailed they can be. They don't have to be single word lexical answer types. All right, so the question is, how do we find them? And we're going to answer this in a few minutes. The second aspect of answering a question like this is that in Jeopardy, there are different kinds of questions. So most of the questions are about facts, okay? So this is a factoid question. But there are also definition questions, multiple choice questions, puzzles, something which is called common bonds, fill in the blanks, and abbreviations. So one of the initial steps has to be deciding what kind of question it is, because depending on the type of question, a different answer strategy has to be used. So for instance, if the clue is a definition has a definition question, then the right collection of sources would be a collection of dictionaries. If it's a factoid question, we would like to go to an encyclopedia or multiple encyclopedias. All right, so here is a list of questions, question types, question classes. All right, so a definition. So here we have an example question, so construction. It can be the slope of a roof or the gunk used to waterproof it. So the answer is pitch, okay? So obviously, we would like to find something, a description like that, a slope of the roof or the gunk used to waterproof it, meaning the roof. If we can find it in the dictionary, then we can take the title element of this particular entry and give it as an answer. So that's essentially what is happening, except for a few modifications. This question would be divided into two pieces. So each of these pieces would separately generate candidates, and then these lists of candidates would have to be reconciled and one of them chosen. Another question, the name of this large beam that supports the joist literally means something that encircles, and the answer is a girder. All right? So again, in this case, perhaps we wouldn't decompose the question, or maybe we would, or maybe we would try both strategies and see what happens. The next is about relations. So, former state governors, so here is Nelson A. Rockefeller, and this answer is supposed to be a state, New York. This is something that can be either retrieved from a textual resource or retrieved from a database. Similarly here, you have 3 examples of a newspaper, and you are supposed to answer with the name of the country, which in this case is Israel. Fill in the blank, okay? There is a quote, okay, and we are looking for the missing element. So in this case, for instance, perhaps retrieving it using a collection of n-grams, or retrieving it just in a passage search might provide us with, with something that can be used to fill in this particular blank. Shakespeare quotes are very common, so we did a lot of work in preparation to the game with the Shakespeare complete works, and I will talk about it a little bit later. Abbreviations, okay, abbreviated SAS. This elite British military unit is similar to the USA's Delta Force, okay? So you're supposed to answer with the Special Air Service. Puzzles, like before and after. This is a specific category where you essentially combine 2 entities and you put them together into something which is Marco Polo shirt, pravda? As an answer to this particular question. Occasionally there are questions about etymology. So from a Spanish for to bake in pastry, it is a South American equivalent of a calzone, and the answer is an empanada. There are questions about verbs, there are questions about translations. There are about numbers, so 1/8 of a circle equals this many degrees, and you are supposed to answer 45. Common bond questions, okay, so edible common bonds, so you know that it's going to be food. So what you have here is monk, snap, and string, and these are names of different kind of beans. So just to finish the list, there are also multiple choice questions. So you are given 3 capital cities, Helsinki, Moscow, Bucharest, and you are supposed to find the one which is the southernmost, which is a difficult geography question for most of the Americans. Oscar, Grammy, or both. Okay, and you are supposed to choose what kind of prize Mickey Rooney got. And finally, there are questions, it's sort of a factoid question, but it's specifically about a date. So World War I ended in November of this year, and it's 1918. So these categories were created in stages. First, looking at a sample of questions. We decided, to divide it into pieces if there was some difference in how we generate candidates or how we answer such questions. So that is, there is no canonical list of question classes. This was used as a guide in processing. All right, so if we know what type of question it is, and very often it's a factoid question. We would like to perform question analysis, and that is find the information about the entities in the question. And we are using for that both rule-based and statistical approaches, and the input is the ESG parse, ESG annotation. Okay, so we are using syntactic or combination of syntactic and shallow semantic information to find lexical answer types, to find the focus. And the result is, well, we perform this analysis in Prolog and then we put it in the CAS. So for instance, this could be one of the rules, a noun phrase with determiner this or these. So in this case, it's a new play based on this Sir Arthur Conan Doyle canine classic. So this classic opened in the London. So essentially we are looking, so the lat here would be classic, okay? If we can connect it to the play, the lat would also be a play or a new play. So with a collection of rules like this, we are able to create, to decide what it is that, that the question is asking about, because it may be obvious to a human, but it's definitely not obvious to the machine. We have to specify explicitly what it is that the answer should be in terms of its lexical answer type. Now, how do these rules look like? Okay, so what we would like to do, all right, when we answer a question like he was a bank clerk in the Yukon before he published Songs of Sourdough in 1907, we would like perhaps to go to some resource where we can find author and composition and the and the author of. Okay, so essentially, I mean, this three-way relation where we have, somebody created something. Okay, that's essentially what we would like to do. We need it for two reasons. One is that some of this information can be specifically specified in a database. So, for example, there are databases of which actor appeared in what movie, all right? There are databases also that specify, the important books and the author, their titles and the authors of them. So if we have this, if we can extract from this sentence that this is what the question is looking for, our answering process will be simplified because we can generate the candidate directly from the database without also needing to completely understand some other text. In practice, we do both. That is, we're gonna do a search on the elements of this query, and that's gonna be discussed tomorrow. But we also gonna try to find it in a database, and then the two collections of candidates will have to be scored. I mean, maybe merged first and then scored. So what do we do? Well, we have certain rules. Okay, when can we have the relationship of somebody being an author of something? Well, if we have a verb of creation in the parse tree, the subject is the author. This subject is, that's basically what it says. The subject is the author, and the object is some kind of a composition, okay, some kind of a work of art. And what are the verb of creation? Well, the part of speech has to be a verb. well, this is sort of just a syntactic thing, that this is also a verb, as that its lemma is on the list of verbs, and this list in this case has these three elements, so it's either write or publish or compose. All right, so we have about 6,000 similar rules like this for different cases, and they essentially assign a preferred semantics to part of the parse tree. So if we have these kind of rules, yes, we can match them against what we have in the class, okay? So from the parse tree, we have a lemma here, the word is he, it's a pronoun, published. Publish is a verb, okay? It matches this particular publish here, and this could be some kind of a composition or work of art. So we can sort of suppose here, we can decide that yes, indeed, in this situation, we have author, composition, and author of together in a relationship, okay? So it doesn't have to be perfect, okay? This detection doesn't have to be perfect, because the strength of this rule, I mean, is not absolute. It's statistical, and eventually, depending on how many things match, how strongly they match, this is going to be scored. And at the end, the scores given by different methods will be combined, and the final score for every candidate answer will be created. So next, we would like to talk about passage scoring. So we have a piece of text. We talked about question analysis. Now we have a piece of text which might contain important information about the candidate answer. We're going to talk about 5 ways of finding a relationship between elements of a question and the elements of the passage. And these are term matching, textual alignment, skip bigrams, logical form answer, candidate score, in short, LFAX, and temporal normalization. After that, we're going to be talking about how we use how we use semantic information extracted from online corpora as another way to score possible candidates and create new candidates. All right, so let's talk about passage scoring. So in passage scoring, we want to understand whether a passage has any information that is relevant to answer a question or provide some information about the answer, validate the answer. So what do? We look for passages that contain candidate answers. So we generated candidate answers using search, and now we try to find the evidence. Okay, and how do we find the evidence? We take the candidate answer, we put it together with the query terms, and then we take a bunch of passages, very often it's 20, and then create a collection of scores for each of the passages, and these scores jointly decide whether the passage is relevant or irrelevant. This combination, okay, of different scores can be either taken by some maximum of some numbers, summing, average. We experimented with many different ways of combining it, and In some ways, I mean, it is important to choose a correct one. In another time, it's not, because you can experiment in parallel with different ways of combinations, and then let machine learning choose the one that seems to be working best. The only problem with it is that it requires a lot of computational power, and that's why Watson has to run on a parallel machine. In the game, it was running on almost 3,000 cores. All right, so we have the example here. On the 27th of May, Vasco da Gama arrived in Kapat Beach, and we have the question here. Portugal celebrated anniversary of this explorer's arrival. As you notice, we changed landed to arrived just for the sake of explaining the method. If it was landed, it would have to add synonyms. So let's assume that we have that this operation of finding synonyms has been performed. But in any case, I mean, the first thing that we can do is to see if there are any direct matches between the passage and the query. Okay, so in this case, I mean, the only string that matches, that appears in both is in, because unless we stem arrival and arrived, these are different strings. All right, so in this case, passage term matching wouldn't work that well. However, if we do a little bit more, okay, what is here written as soft matching, that is, we know that arrived comes from arrive and arrival comes from arrive, and we can detect it automatically. Now, if we knew that we should subtract 400 from 1898, then we could also have a match here, because we also have a May mentioned in this particular thing. Oh, actually, there should be another match. Yes, May. I don't know why it's not depicted here. All right, so that's essentially what the term matching does. All right, so the term matching essentially counts how many terms are the same in both the question and the passage. And if the higher the overlap, it's more likely that the passage is relevant. So the second procedure is textual alignment. So what, based on order mostly, and sometimes based on predicate argument structure, this is going to come later, we will try to align, the question with the passage. So what would match? Well, what would match would be this, yes, okay, dates match. Here we have someone mentioned. This person could be an explorer. Arrival matches in matches India and Kapat Beach, okay? So again, we could assign some kind of a score for this alignment, and the direct alignment here is that yes, Vasco da Gama could be an explorer. We could check it, for instance, in an encyclopedia, and again, if we have some way of dealing with anniversaries and dates, we could have a soft match here, and if we could check that Kapat Beach is in India, we would also have a match between India and Kapat Beach, all right? So we do not have anything about celebration here. We don't have Portugal mentioned. So this is, so again, the score will be imperfect, but it will provide some evidence for this passage. All right, the next method is similar to the one before, except that we are allowed to skip one word. So basically, we look at this question and the answer as a collection of bigrams, and we are trying to do the matching. So in this case, what do we have? We have arrival connected to the date. We have arrival connected to the explorer if we skip one word. And let's see. And then we could match explorer with Vasco da Gama, in with in, and these particular dates, okay, assuming that we subtracted 400. So the moral here is that if the graphs look somewhat similar, we assign it a higher score. The next type of matching is uses the logical form. So in this case, what we are interested in is a situation where we are asking a question, for instance, who invented a telephone, and we have a passage which we seen before. Say Bell invented telephone and somebody else invented quantum mechanics or relativity theory or some other irrelevant information. But if we can match invented with invented, subject with who, and these two things match, telephone with telephone, then this matching provides a good argument that this is the Bell who it's Bell who is the inventor of the telephone. But in complex domain, these matches are almost never perfect. Okay, so what we do is we essentially give partial credit depending on, for instance, how many nodes do we have to get from the verb to the subject. So that is the Elfax algorithm. All right, so altogether, this allows us to create a match between the structure of the question and the structure of the passage, where arrival is matched with landed via synonymy, via temporal link, or special treatments of anniversaries and dates. We are matching these things. We are matching Explorer with Vasco da Gama via the subject link. So subject is matched to the subject. And then in India and in Kapat Beach are also potential matches. So if we can find out that Kapat Beach is in India, this provides us with the evidence for the match. All right, so here is another explanation of this L-Fax match, where we have Bell invented the telephone and Einstein discovered the relativity. I think I should have had this slide earlier. All right, so we already covered it, that essentially we are looking for a graph match, and based on the fact that Bell is the subject of invent, and in both of them have the object, we can score Bell high, and for the same reason, the fact that, you know, Einstein discovered the relativity, it's a different verb, different object, different subject. We would not take Einstein as a good candidate here, or as the, okay, all right, so we evaluated these methods, okay, and what you see here is essentially the curves that plot the value of using these methods, okay, so what you see here is, okay, what you see is the dots denote performance of Jeopardy champions, okay, and so this is the cloud, this is the winner's cloud, and to win the game you have to, well, you have to be somewhere in that cloud. So this purple line shows the performance of the system without this particular collection of algorithms. However, once the algorithms are added, okay, this suite, the performance goes up by a few percentage points. So that's something that really makes a difference in the game. You know, a few percentage points actually is important because, you know, some of these people play really, really well. All right, we partly covered, oops, well, this is, all right, I don't know why this is not projecting here properly, but basically the purpose of this slide is to say that yes, that there is a standard way of representing dates, and there is a rule-based anniversary detection system. So 1898 and 400 would be put together, and a new reference date of 1498 would be created. This is a list of main algorithms that I used to do natural language processing in Watson. Okay, so slot parser grammar, so we discussed parsing before, and in particular we've seen some examples of how slot grammar parser performs. We had a discussion of predicate argument structure. Slot grammar also provides us with some entity detection, which is then augmented by another module which does named entity recognition, that is finding people, places, works of art, compositions, actors, films, and that kind of stuff, which is important in answering questions. We talked yesterday about doing reference resolution, and in particular finding the references for it, he, she. Today we talked a little bit about temporal normalization, so basically dates are represented all the same way, so it's easy to check if they match. Temporal arithmetic, for instance, finding the anniversaries. And we will talk now about finding certain semantic relations in two different ways. So what do we do to find semantic relations? Okay, to find semantic relations, we either have a collection of rules as that you have seen before, and they are based on the shape of the parse tree and some of the attributes of the parse tree. Or we use some statistical methods that we're going to talk about in a few minutes. Okay, and these are used for answer lookup, passage scoring, temporal scoring if the answer is a date, and geospatial scoring when we have to do something about geography. So what are these relations? Okay, so we saw before the relation of being an author of some composition or a piece of art. So we also have actor in a movie, actor of, I think this is about the character. This is author of a work, director typically of a movie, creator of something, so it's more general, playwright, performer, composer, and some piece of work here. And then with people, a person can be born somewhere on certain date, certain nationality. So we try to detect these kind of relations because they play a role both in understanding questions and in answering them. There are some relations which appear often enough in jeopardy that they are worth formalizing and creating rules for detecting them. So, like, award type, which could be an Oscar, so somebody got an Oscar award. Movie based on a novel, okay, so title based on a title. Maybe party affiliation, say for the US presidents, yes. And then many questions deal with location of a city or a river or some other geographic entity, and then there are questions about who borders, which country borders which, or which one is the southernmost. The sources that we use for finding these relations and basically storing them separately as relations, I mean, the main source is Wikipedia and DBpedia, which is also something you can get together with Wikipedia. So this has a format, more database format. This is textual, but we can extract such relations automatically using a collection of mathematical methods. Finally, we extract relations statistically, essentially from all the text that we have. We looked at the syntactic frames such as subject, verb, object, subject, verb, object, prepositional phrase, so something about a location, for instance, or a manner, or time. So we parse these volumes of text, we extract the syntactic structures, and then we run a lot of statistical analysis to find patterns that repeat very often. So for instance, such a pattern could be that an inventor patents something, an invention, a new device, a new mousetrap, yes. From newspapers, we often have something about an official submitting a resignation, all right? You can earn a certain degree at school, so be it a master or a PhD. You will learn relations that, some synonym relations, like fluid is a liquid and liquid is a fluid. You learn facts that very often vessels like Titanic sink. And then, that balls can sink in a pool or something like that. So there is quite a bit of stuff that can be extracted automatically. All right, so we call this system prismatic. It is a large-scale resource. So we process hundreds of gigabytes of data. We do parsing. We do named entity recognition. So that comes both with the parser, with some additional method. We try to do coreference resolution. And once this is done, we are ready to essentially look at these subject-verb-object relations, but look at them semantically. So here's an example. So in 2005, Marino was inducted to the Hall of Fame for his tenure in Miami. So from this, we would like to find the relation of being inducted in the Hall of Fame and the year. And essentially, this is done based on this collection of syntactic relationship and the coreference resolution that happened between Marino and his. So the frame number one, which I don't, is it readable? Because I can't read it from this angle. Okay, so basically the frame number one has the verb induct, the object is Marino, and type is given as person player. And then we have in 2005, where 2005 has a type year. And then we have the modifier 2, and object is Hall of Fame, which is understood to be a place. All right, so that's essentially what we can get out of this particular sentence. And then we also get another frame, okay, which is that there is a tenure, okay, which is modified by Marino, which is a type of person player. So person player tenure, and then there is a relation in Miami, which is place. Okay, so that is probably a less useful frame unless we can find some other frames like this and generalize from them. Okay, so this is the repetition of the same process. So how do we perform generalizations? All right, we found this one element and we can store it perhaps as a fact, okay? But we also can generalize that since we know that Marino is a person from named entity recognition, we can create a pattern that person can be inducted in a year and person can be inducted to a place. I'm not sure that we can do anything with this. And that we also get a pattern about a person having a tenure in a place. So we can then try to automatically find these kind of relations and store them for a lookup when we have to score answers or find answers to questions. So in this case, what the diagram shows is that from about 50 gigabytes of data, we extracted about 1 billion such frames, so quite a large number. All right, so where is it used? Well, we are using it to decide, to answer questions where, is vein a vessel? Okay, do we have any examples that would suggest that a vein is a vessel? Assuming that something like that, appears in the question. We can use it to generate candidates, okay? So we can see which animals have a relation to a farm, okay? And that is probably a finite list. And maybe we can also see if there is some relationship about a Morocco animal. So all of that is something that can be done by querying the prismatic database. And finally, we can use it to find some hidden information. So this is really not readable So I'm going to read it from here. On hearing of the discovery of George Mallory's body, he told reporters he still thinks he was first, okay? So this is not an easy question to answer, all right? Because essentially what we are looking for is we are looking for the answer Edmund Hillary, okay? So how do we get, how do we get to Edmund Hillary from George Mallory's body, okay? If we find the information, a link between Mount Everest and Mallory, this allows us then to postulate another link between Edmund Hillary and Mount Everest, and then probably somewhere else we can find the information that, there was another link that Edmund Hillary was first on Mount Everest. So some numbers here. Well, here we have another version of this data where we have 30 gigabytes of data, also 1 billion frames, 1.4 frames per sentence. Most of them deal with named entities, and that shouldn't be surprising because our corpus is sort of very heavily skewed towards encyclopedial type entries, and the value of it is about 2.5% in accuracy. So what perhaps you notice is that none of the methods that we discussed so far was really providing us with a huge boost in performance. So most of the performance improvements when we were creating the Watson system came from tweaking algorithms, finding new algorithms, and adding new sources. We're going to be talking about adding sources shortly, but the point is that it shouldn't surprise us that, that a relatively complex method that produces about 1 billion pieces of information gives us only a 2.5% inaccuracy in terms of improvement. The reason for that is language is complex. We really don't know how to do it, so what we are doing is essentially throwing a lot of information. We are putting some structure on this information, so it's not a complete chaos, but the results are likely to be modest from any of this method taken separately. On the other hand, when we combine these methods, we do get a significant improvement in accuracy, and this is what allows us to win the game. So this is a diagram that we've seen before, all right? So we get the question, we do question analysis, which we discussed a moment ago. We do hypothesis generation, which comes mostly from search, and we're going to discuss later. We talked a moment ago about how we use these different methods for hypothesis and evidence scoring. Okay, we haven't talked yet about what we do to assign the final score, but that part, while non-trivial, is less related to natural language processing. It's more about machine learning. All right, so we discussed so far question analysis, evidence analysis, finding relations, and using these relations. So now there are two natural questions. How do we prepare the data? And then, how do we generate the candidate answers? So for data preparation, we will talk about corpus selection, preparation, and transformation, and then about corpus expansion. And then about finding candidate answers, we will talk about the process of search and candidate generation. So for search, we're going to introduce some preliminaries to let you understand how the search engines work, at least to give you some intuitions about it, and then we will talk about how we actually use them. All right, so let's talk about processing of textual sources for question answering. We will cover types of sources, how we prepare them, and then discuss the impact of these sources. So 3 points, yes? Obviously, text can be a source of knowledge, okay? We all use Wikipedia and other textual sources. We know that there is a lot of interesting information there. So naturally, we should be able to use it in trying to answer Jeopardy questions. But machines are not humans, okay? They do not read, so something has to be done. I mean, these texts have to be organized. If you look at the raw encyclopedia web page, yes, the raw Wikipedia web page, it's not pure text. There is a lot of other stuff. There are various annotations, you know, different fonts, pictures, information coming from DBpedia. So we need to make sure that, you know, that the text is usable for the computer, okay, that it can be indexed, and then if necessary it can be searched and processed by other modules, in particular by the parser. And the final point here is that the computers use text differently than humans. So in particular, a computer can sift through a huge amount of data and find out whether, you know, a name, a date, or a relation is explicitly mentioned there. People can't do it, but people are very good at finding, for instance, some implicit connections, and that is very difficult to do for the machines. So what we gonna show is how we can replace this human intelligence by just adding a volume of data. So that will be part of this lecture. All right, another version of the architecture slide. So we're gonna focus now on preparation of sources. So we need to prepare sources for search and candidate generation, and then we need to prepare sources for evidence retrieval and scoring. The good news is that these are basically the same sources, or most of these sources are the same, so therefore the preparation process, at least the initial preparation process, is common. And then what happens here is that to speed up the use of these sources as evidence, we parse them, and we do some of these prismatic-like operations on these sources, and we store it in a separate database, while, after a little bit of preparation, these sources, the original sources, are simply stored, are indexed by a search engine. So how do we use text as knowledge? Well, it's obvious that Wikipedia has facts, and dictionaries have information about various syntactic phenomena and definitions, and they could also provide us with some shallow semantic information or synonymy information. However, in practice, it's not necessarily easy. So there was work trying to to assert whether just adding additional data would improve the performance of a question answering system. So just, providing redundancy, does it work? All right, so in 2002, there was a paper written where the experiment was about, how much data do you need to add to a 3 gigabyte corpus that was used in some government question answering competition. And the answer was that, well, that you need 50 gigabytes compared to, to the 3 gigabytes of the original corpus, all right? Moreover, if you added too much data, the performance degraded, okay? So it is very difficult just to throw data, throw additional text on the machine and expect that the performance will improve. That doesn't happen. It has to be done in a more controlled way. In our case, all right, we had to create a standalone system. So, for instance, we couldn't rely on the internet to find additional information. And we needed to provide very fast answers, definitely below 3 seconds, often, below 1 second to be competitive. So we had a limit on the amount of text that we could actually use in the system. Therefore, we tried not to add the data that didn't have any impact on performance. So the first thing that makes Watson different from other question answering systems and from the way presumably humans operate is that we decided early on that we're going to use titles as answers to factoid questions. So in other words, we would go and, and we find the article which has the keywords, yes? Then presumably one of such articles which will have a title, and this title is the answer to a factoid questions, because presumably Wikipedia will have all these facts already, all right? That was, that was the hope. There was quite a bit of evidence that that's the case, but it wasn't the full answer. So we needed to add some additional sources. So what we did, we were going through some iteration of steps, which was deciding which sources we should acquire, so either license or download, then decide how they should be processed, okay, before we put them into a search engine. And then many of these sources could find more than one use, okay, or sometimes to find any use, we had to transform them. And finally, we also decided that, not all information can be found, say, in encyclopedias that we could license, or dictionaries, or, or properly edited sources. So we went to the web and tried to find snippets of information that could be added to, to the original articles to fill the gaps in Watson's knowledge. And all of that was done in parallel with the process of error analysis, that is estimating and analyzing impact of all these steps. And we're going to talk about how this was done. All right, so how do we use title-oriented sources? So the initial observation was that if we take 3,500 questions, okay, then 95% of the answers were actually Wikipedia titles. This is misleading because Wikipedia titles, for instance, exist for all numbers probably from 1 to, I don't know, at least a few thousand, if not a few dozen, if not, say, first 50,000. So if there was, say, a question about doing some fast multiplication or fast addition in jeopardy, or a question where, you know, the answer was 45, meaning 45 degrees, well, there is definitely a Wikipedia article which has 45 as a title. Nevertheless, in other cases, yes, the title was there, and in many of these cases, the title and was a good answer to the possible question. All right, but it doesn't mean that, say, if you were to run a search with your query, with your questions, with your clue, and you submitted it to the search engine, that this particular title would come as, you know, as the first answer, or even if in the hit list of the first 50. It just means that somewhere there, you know, the answer was in the, you know, among the Wikipedia titles. That shouldn't be surprising also for another reason, that there is about 4 million of Wikipedia titles, so it pretty much covers the whole vocabulary, all right? So, well, but if that's the case, okay, if we can find any answer as a title, so maybe this should be a strategy, and that's what we tried, and it started to work reasonably well. Okay, so for instance, if you have the question, the first US men's national singles championship played right there in 1881 evolved into this New York City tournament, okay? And the answer here is tennis. Sorry, this is the category, tennis, and the answer is US Open, yes? So, these facts, presumably, are in the article about the US Open, okay? So, in another way that we can use a title-oriented resources, if we have a question like Aleksander Kwaśniewski became the president of this country in 1995, well, we can take this entity, yes, and find here the answer, find here another named entity, and this is, you know, a name of a country, yes. So we can generate, you know, a candidate, and maybe we can then score this candidate using the methods that we discussed before by taking a passage from the article on the history of Poland from 89 to the present, and there we have, you know, Kwaśniewski first presidential election, so we have sort of Aleksander Kwaśniewski strongly associated with president, presidency, and presidential election. All right, so this is evidence that indeed, you know, Poland would be the right answer to this particular question, and we are essentially finding relevant information. All right, so the original system, which was one of the best systems for question answering, but didn't use titles as answers, okay, that was essentially the performance. So that meant that if we answered 50% of questions, that only 15% of these questions were answered correctly. If we tried to answer 90% of the questions, the performance was you know, around 12%. So once we decided that we're going to look for titles as answers, all right, the performance started to look more reasonable, okay? So this was the huge gap, just taking titles as answers and keeping the rest of this system constant. But that was not nearly enough to play a competitive game, all right? I mean, not just from the point of view of how many questions you have to answer. Well, you really have to answer, you know, say 70% of the question, and you have to be 90% correct to play a really competitive game. So everything else after that essentially came from various algorithmic improvements and adding new sources. So what you see here is how these curves changed over time. That was probably one of the last, if not the last curve that we recorded before the game. Okay, the game took place in January of 2011. It was transmitted in February of 2011, and we had to freeze the system a few weeks, before the real game, so that that the code would be moved to the machine that actually was doing the playing from the workstation systems that we use for development. So, titles as answers, yes. So we were not looking for relevant sections with answers, which was the dominant practice. Later we had to sort of qualify that, okay? Yes, we actually do look for passages if we can't find the answer in the title, if we have no good strategy of, if the search comes with nothing because of the statement of the question. So we do look also in some other sources, but the main strategy is to answer factoid questions is to look for titles. All right, so we have this process of source selection, pre-processing, transformation, and expansion, and the process of error analysis that goes in parallel. So what does it mean to do error analysis? Essentially, it means to run the system on a collection of questions. Sometimes the questions are known. This is the development set. Sometimes the questions are not known in advance. And then that this is a test set, okay, that we use. As you can see from here, we run about 8,500 experiments as of February 28, 2011. So there were, dozens and dozens or hundreds and hundreds of experiments that were testing different parts of the system throughout the life of the project. So probably 3 years, because I mean this error analysis tool existed for about 3 years prior this date. All right, so what you see here is different experiments with different numbers, with different dates sometimes. And what you do is you compare the results of such experiments, and you have presumably do it on the same corpus. So you have a number of questions, so 3,500 questions. You look at how many of these were answered correctly if you choose 70% best. So this is about 80%. If we were to answer all questions, 63% were accurate, and you see the difference between these two experiments is about 10 percentage points in accuracy. All right, so that way, if there was some change made to the system, you could decide whether this is something that's working or something that's not working, and you could drill further down to see, for specific questions, what happened to the answers. Okay, are they still correct? So here you see the numbers are still the same. The correct answer is number 1. Here the correct answer is number 2, but this particular word, adultery, is not the correct answer to this question about crime. But what's more interesting is that the confidence factors changed. So here the confidence is almost 1, 0.96, and here the confidence is only 0.82. So presumably some of the scorers are confused. So we can drill further down and see which scorers contributed to this particular change. and decide whether we want to keep the change or decide that, that this is not something that has any promise and abandon a particular algorithm. So once we get a source, yes, some sources come with their titles, and essentially the only thing we need to do is to detag them. So remove all the unnecessary formatting and put them into the format that we use for indexing. Okay, this format is called the track format, and we have an example of it here. We're going to go through it in a minute. Before we do that, I want to mention that some sources are not title-oriented, okay, but we still need to do something about them to put them in this track format, because we decided that we're going to be answering questions based on titles. So what it means is that if we have a complete collection of complete works of Shakespeare, then we have to divide this collection into a collection of title-oriented documents. So for example, what we did here is we created a document which contains a line, a few lines spoken by Ophelia, okay? And this is from the Shakespeare collection, so we have a document number with some name for the collection. This is the number 211. The title is Ophelia. We have the text, and actually, what would happen is that all the lines spoken by Ophelia would be gathered in this particular segment, all right? And then the same exactly lines, the same collection of lines could also be gathered under the title Hamlet, because that comes from the play Hamlet, all right? In yet another version of this work, the title would be Shakespeare, because we would subdivide the Hamlet into several documents, and all of them would have title Shakespeare, because sometimes there is a quote and the only thing you have to name is the author. The reason that we did that we divide say Hamlet into 10 pieces is that the performance of the search engine is better if the documents are not very big. So we did the same thing with the Bible, important books, with smaller works like slogans of IBM marketing campaigns, but also with song lyrics, where we had several versions depending on, in one case it could be sort of the band, in other case it could be the title, or yet in other case it could be perhaps the name of the album. We did the same thing with selected poetry works. So all of that was for the sake of keeping the strategy consistent, that is answering by the title, okay, the title being the answer. And that's not something we could have gotten from Wikipedia, so that had to be done as a separate piece of work. Well, another part of transformation was that Wiktionary, which is a dictionary that is open source and relatively complete, might have two entries for program, one with the American spelling and one with the British spelling, but not necessarily with exactly the same definitions. So since the Jeopardy game is an American game, we wanted to standardize on the American spelling, and therefore we would have to detect that these two guys are essentially the same entry, and then combine essentially use this as the title and add all these definitions to the body of this particular title. Other issues that were encountered were that Wikipedia uses first name, last name conventions, but some of the other sources that we had was the convention was different. So it was, for instance, last name, first name, and then some title, like, you know, like Earl of Edinburgh or Duke of Normandy. So we had to detect these and then drop them, but not drop the information. So what I would do in that case, for instance, would be to keep the information and add it to the first paragraph of that particular dictionary entry or encyclopedia entry. We normalized dates, so 08, depending on the context, could be 1908 or 2008. So that was also done in the process of preparation of the resource. We created new sources, okay? So, for example, we took famous books from the Gutenberg.org website, which contains books out of copyright, and we created a resource which contained all opening passages of all chapters of these famous books, just because sometimes the questions might quote a well-known piece of work and ask who is the author. Similarly, to answer questions about proverbs, we extracted a collection of proverbs from Wikiquotes. We have built a language model that was used to score the distance between a candidate answer and query term, okay? We used for that a collection of 5 grams. And what we did there was that we used a Hadoop cluster of about 50 machines to process 200 gigabytes of text. It was detagged and pre-processed into paragraphs, and we experimented with various frequencies, with various orders, so we took the words either in alphabetic order or not. We created different collections of such n-grams because people experimented trying to do something with prepositional phrases, but in many other applications, for instance, in scoring, the presence of prepositional phrases is irrelevant. And finally, we used both term-based n-grams, in which compound phrases like the White House were treated as one unit, and word-based n-grams, in which such phrases would be treated as separate units. In the final system, we used term-based, alphabetized 5 grams as a collection on the basis of which we did some scoring. The result was that we tried to do the same thing, the same kind of application using a collection of Google 5 grams, but this collection was too big, okay? So by essentially carefully choosing the text that is relevant for us, we managed to achieve a 10-fold reduction in size in terms of the number of these 5 grams, in terms of how many gigabytes of data that they took, and achieve the same performance as a collection of 5 grams that would be 10 times as big. So what remains to be talked about when it comes to data preparation is corpus expansion, all right? So basically what we want is to get some quality data from the internet, from the web, add it to our existing resources to fill the gaps, both in terms of factual data and in terms of how these facts are expressed. But we don't want corpus degradation, okay? that was observed before in the paper by Clark and others that we discussed a few minutes ago. So how do we do it? Well, we start with something which is a seed, okay, that we want to expand. So this could be a popular Wikipedia article, that is article that people actually click on. We couldn't afford to expand all Wikipedia articles, which would be about 4 million. Instead, we focused on the ones that people are most likely to click on. This information is available from Wikipedia, so we expanded, I think, about 100 or 150,000 such articles. What we do then is we perform a query. We get some web pages that might be relevant to this particular Wikipedia article or its title, and then we look for pieces of this of the text on the web page, and we try to score them automatically and keep the ones that are best. All right. And once we have them, we can append them. You can create a new document with the same title as the seed title, and use this document. This document would be used by the machine, not by a human, so it doesn't have to be consistent, complete, well written, or anything like that. And finally, since we don't want to add too much stuff, we have to see if this procedure produces any reasonable results. So how is it done? Well, the process consists of taking a seed document, so in this case it's about Tourette syndrome, going to the web, performing a query, and finding 100 documents which come as a result of query Tourette syndrome. So any search engine presumably could be used for that. We used Yahoo because it didn't have any legal conditions that would prohibit us from doing so. Okay, we actually explicitly got Yahoo's permission to use their search engine in that particular process. And then we divide each of these documents into pieces consisting of a sentence or a couple of sentences, and then we score them as to whether they are relevant or not. So for instance, here is an irrelevant passage which was perhaps an advertisement on the web page, which talks about, some deal on a book, if I'm not mistaken. The book will be shipped mid-June. If you pre-order, there is a discount. Yes, okay, so this is not relevant, so we don't want this part, but perhaps the other passages are relevant, so we put them together into one merged document. So the natural questions are, how do we know that this is not relevant, and how do we choose the best passages? Okay, because perhaps there is just too much of the relevant data. All right, so we attempt to increase the coverage, adding new information and lexical and syntactic variation that is extracted from this large external collection. So what does it mean? We're going to be looking for something which is relevant, but it cannot be exactly the same because we want to add either new information or it has to be expressed differently, okay? So it cannot be, it could be a syntactic variant, but it cannot be the exact quote. So we are looking for additional facts, different expressions of a known fact, and a new way of arranging information about topics. So for instance, known facts in Wikipedia can be grouped differently. They can appear in the same paragraph in one of the nuggets of the expanded corpus. this is the statement of the algorithm that we described when showing the diagram on the Tourette syndrome. So we start with the quality seeds. We go after the combination of nuggets. We score these nuggets. We create these new documents, and we evaluate the corpus. So let's talk about it a little bit. All right, so we create seed documents. So, for example, if we were to extract, to create a corpus expansion algorithm, corpus expansion system for diseases, yes, we could just extract Wikipedia diseases and perhaps only a symptom section of Wikipedia diseases, all right? So there is no reason to take the whole article. Very often it's enough just to take, you know, a part of the article, a beginning, because it is likely that the beginning of a Wikipedia article will have the most relevant information. Then when we retrieve, we go to Yahoo, so we perform this Yahoo query. Boss is the name of the Yahoo interface. We get about 100 pages, okay? And our query there is usually a document title. So for instance, it could be influenza, okay? If this is a disease, for instance, and we want, you know, the whole thing about diseases. If we want to know only something about symptoms, we would do a query influenza symptoms. When we were doing Jeopardy, our query, we experimented with different kind of queries. In one case, the query was just the title. In another case, we added some additional words like trivia, because very often we were missing some, funny information that existed on some web page, and very often this information was had a title like physics trivia, math trivia, pigs trivia, New York State trivia, and that kind of stuff. So the query, the query doesn't have to be exactly the title, but it has some connection to the seed document. The extraction process is actually non-trivial, because first of all, we have to get rid of all HTML tags. There is no way of doing it reliably. All existing systems perform make quite a bit of errors. Then we need to split documents into smaller chunks, and again, sometimes it's possible, sometimes it's very difficult. In many cases, the nuggets are too small. In some cases, the nuggets can have, say, 8,000 or 10,000 characters or more. Many web pages contain spam, all right? So all of this stuff makes this process of extraction relatively non-trivial. Nevertheless, what we do is, we do our best, and we assume simply that just from the volume of the data, we will be able to extract something that has some value, even though we know that a lot of the stuff that we're going to extract will have no value, and it's possibly also detrimental. So as long as it's not too detrimental, we're going to be fine. Okay, so there is some length of the nugget which is optimal. We don't know what this length is. Very short nuggets will not have much information. Very long nuggets will have too much information, and a lot of this information will be irrelevant. So therefore, we use length of the nugget as one of the possible parameters, and we're going to talk about the parameters in a second. So to score the nugget, we have a statistical model, and we essentially try to decide two things. One is the nugget relevant in the sense that it matches some portion of the seed document, okay? Say it contains the same words, yes? So or it has a similar language model that is, you know, the numbers of words are the same or uses the same bigrams, so that kind of stuff. And also a collection of other parameters in the sense that, okay, is this nugget of the length that good nuggets have, okay? So we have, you know, we can learn the optimal nugget length and use it also as one of the scores. And then we have 8 to 15 such measures, and they are aggregated using logistic regression. So essentially using a weighting function that would provides us with the final score. And finally, you know, once we have the nuggets with score, we have to decide what the cutoff is. And typically what we do is, you know, we look at the collection, we see that, say, maybe the nuggets scored 0.35 or higher look reasonable, and there are not too many of them. So we have essentially an arbitrary cutoff number that allows us to take a collection of nuggets, not make this collection too big, and still have a positive impact on question answering. I think I'm going the wrong way here. All right, so here are the scoring features. So this is the language model score. So essentially we are looking, you know, how similar the nugget is to the seed. This is another language model score, which is just computed in a different way. It turns out that average TF-IDF score of the tokens in the nugget could be, you know, could have some value. This is a common type of measurement that's used in information retrieval. And the motivation is that tokens with high TF-IDF scores are often central to the topic. So in other words, these are essentially high content words are more relevant. We look at titles, okay, so if the title tokens appear in the nugget, that usually is a good sign. It turns out, I don't know, it could be an accident, but if we have third-person pronouns, that very often such nuggets are relevant to the topic. This could be just because Wikipedia has quite a few articles about people and quite a few articles about you know, different places. So therefore, the use of he or it or him or her is relatively common. I'm not sure that this is necessarily, say, a good measure for scoring medical nuggets. Search rank, so more likely the documents that were retrieved, you know, as top hits are more relevant, and this was confirmed by experiments. So all of that, you know, so we have a collection of such measures. I mean, the exact explanations of, you know, what's happening here is has been published in the papers. I'm not going to go into it, but basically what we do, we have to aggregate these measures and then provide final score for each nugget. And after we do that, yes, we have this collection of nuggets, and we can ask a question, okay, does the you know, if we add a collection of such nuggets and we try to answer Jeopardy question, is the performance better or not? And the answer is yes, the performance improves. It improves by a couple of percentage points. I mean, there is some detailed analysis both on Jeopardy and on track collection, which is sort of a collection of government-sponsored competitions in question answering. And in both cases, we have, you know, a substantial improvement in terms of the quality of answers. This improvement comes at a price, though. So if you look at the last line here, okay, we have to more than double the collection of documents in terms of the number of, you know, of characters to get, you know, a substantial improvement from corpus expansion. So let's talk about it a little bit more in the detail. So what you see here is that here's the answer essentially to the following questions. Okay, could we do Jeopardy only with Wikipedia? Okay. Was it worth to do all this source acquisition and transformation? And, you know, how much do we get really by corpus expansion? Okay, so these are the numbers. So the answer is that Wikipedia is a lot, but not enough. We really had to be, you know, 70% accurate or higher to be really competitive in Jeopardy to win the game. So that was, you know, so all of these steps were necessary. Whether we would have achieved, you know, this additional 4% improvement without corpus expansion just by adding perhaps some additional sources, I don't know. I mean, I think that we gained quite a bit new information by going to the web. As you see here in the candidate recall, yes, with Wikipedia only, despite the fact that 95% of all answers are in Wikipedia title, when you try to generate the candidate, we can only generate about 77% of candidates. And we do have to be, again, somewhere between, you know, 85 and 90 to be competitive in the game. So Wikipedia, again, is not enough, although together with these additional sources, so, you know, additional quotes, proverbs, different encyclopedias and dictionaries, lyrics, poems, and Shakespeare and Bible, all that kind of stuff does, you know, takes us more or less to a competitive performance. This line in the middle is about, and we have to answer about 70% of the questions, and we have to answer them well, okay? So with Wikipedia, our performance is around 77%. Here we are 87, close to 90%, and that is enough to be very competitive in the game of Jeopardy. So what's the price that we are paying? Well, we have to have more documents, yes, as we go from Wikipedia, which was at that time about 3.5 million titles, to additional sources, okay, so other encyclopedias, other resources, you know, 3 times repeated Shakespeare works, lyrics, all that kind of stuff. So that's about a little bit more than a double. And then corpus expansion doesn't really produce that many new titles. So no, you know, there is 2.2 new concepts, perhaps, yes, new titles, but it more than doubles the amount of information, all right? And altogether here we have, you know, we have a fourfold increase, more than fourfold increase in size. So now, if that is our collection, yes, and this collection has to be processed, parsed, and then accessed in real time, the size of this collection essentially determines that we need to use a parallel machine. So a few words about corpus expansion for medical diagnosis. All right, we have run some experiments in that space, but the experiments are somewhat promising. But what I want to talk about is the fact that these documents, okay, have a more complicated language than Wikipedia documents, and matching, okay, you know, some of these scoring methods that we used will likely to be adjusted, okay? So here we have a seed document about herpes simplex keratitis, which is a viral infection of the eye. All right, we have, you know, collection of symptoms. We have some other statements. So this is our seed document, and we would like to expand these seed documents by adding additional information. So here we have a nugget, which is scored 0.6. It has certain URL associated with it. So this is, you know, the website we got it from. And, you know, and it has relevant information about herpes keratitis. Here we have a nugget which shares some of the same words, but it is about something else. It is about herpes simplex, which is also a viral disease, but a different disease. Okay, so we would like to score it lower. Here is to show that it's possible to get high scores on an irrelevant article, again, because many of these medical terms are shared between, you know, between the seed and this particular document. So for instance, I mean, if we do an analysis of such a collection of nuggets, we can find that, you know, that in this particular trial, I found 48 nuggets ranked 0.3, which I used as a threshold. I found 33 good nuggets, which is good news, but 12 of them were confusing, like the ones that you saw before, which had high scores but was irrelevant. And some of them just didn't have any interesting information, so they were not harmful, but they were just taking space. So it is likely that to do something similar, either in medical domain or in the domain of, say, help desk support, or in finance, where, you know, some companies are interested to do it to create a Watson version for finance, we would need to improve nugget scoring to account for the difference in the domain. All right, so what are the morals of this story? That we have methods for using corpus expansion to improve the accuracy. Such method improves both recall and accuracy. It does not introduce too much noise into the text corpus. And such a method can also be applied in a new domain, such as medical diagnosis, although it's too early to tell if this is the way to go. Again, I mean, the same slide about source engineering that we've seen before. So we get to champion performance by doing both additional source acquisition and transformation. Wikipedia is not enough. We pay the price in terms of the size of the corpus by doing corpus expansion. But again, we don't have to go to 500 gigabytes of data. We only have to go to 60 gigabytes of data. Another thing that I want to mention is that, that this performance around, 87, 95%, we've seen it also in other places, that once you achieve this kind of a level of performance, people see it as human-like, okay? So we've seen it before when we were experimenting with natural language dialogues, for instance, for either information finding, for buying IBM laptops when IBM was still saying laptops, and for phone banking, all right? That if you get to 85, 87% correct, people really begin to like it. So how is text used as knowledge? All right. Well, Watson was a milestone for NLP, okay, in terms of language processing. It achieved the first open domain competitive with human question answering, all right? But a large part of it was related to source engineering because, as we have seen in these tables, it led to improvements in recall, precision, and accuracy. We have created a whole process for source engineering consisting of evaluating knowledge gaps, using title-oriented formats of answers, doing various ways of source transformation and corpus expansions, all of that as in an iterative process of monitoring the impact of all of these steps. We believe that these methods are applicable to new domains such as medicine, finance, and help desk support. So in the final part of today's lecture, we're gonna cover the basics of information retrieval. These are preliminaries needed to understand how Watson search and candidate generations are working. So we're gonna present a few examples and cover some of the vocabulary, and then talk a little bit about the INDRI search engine, which is the search engine, one of the two search engines used by Watson. So obviously we have all seen examples of search engines. A conventional library catalog is, if it's electronic, it's a search engine where you can search by keyword, title, and author. Although obviously we more often use Google, Yahoo, Bing on the internet, or people who have to do legal searches use a specialized search engine such as LexisNexis. Usually such searches are performed by keywords, and it is difficult to create a search engine that would give you the right documents or answer questions in natural language. Some of the search engines, such as Bing or Google, also allow you to search by visual appearance. So you can search for photos, you can search for diagrams, you can search by certain colors. But for instance, you cannot search by the description of the picture in your own language. If the picture is described by somebody else, then you might be able to find it using sort of a textual search, but the machines are not good enough to connect the content of the image with the description of the image, that is to understand what is in the picture. Then there is Watson, which is a question answering system which is capable of answering mostly factoid questions, but in unrestricted domains. And in addition, when we talk about search engines, we often talk about programs which allow us to build a search engine. So such systems are INDRI and Lucene. INDRI is part of the Lemur project, which is sort of a university project in the US aimed at building new tools for information retrieval. Lucene is an open source search engine which has many commercial uses. And again, I mean, it is something you deploy, for instance, in the enterprise, then you index your own collection, and this is how you create your enterprise search engine. So what does it take to build a search engine? Well, you have to have something to index. Usually it's text. You have to gather it, perhaps prepare it. Then you run the indexer on it. Then you have a problem of what happens if you know, some documents get obsolete and new documents have to be added to it. And finally, you have to provide some ways for the user to do a query and retrieve a good result. This is easier on the web, where the web pages often have cross-references to other pages, and this can be used, for instance, to find the most popular pages. In addition, there is information about, you know, which pages were clicked on in response to the Google or Bing query. So all of that makes web search a little bit more user-friendly than, say, the enterprise search, where this kind of metadata is often missing, and therefore the quality of such searches is not necessarily so good. There is a certain vocabulary that is used in information retrieval. So a query means is a representation of what the user is looking for. So typically, say in Google, it would be just a collection of words. But say if I am searching a patent database, I can put you know, some additional words there, such as Boolean connectives and or I can put I can do a fielded search where I can look for patents owned by IBM. Okay, so I could put the assignee to be international business machines, and then I can search by keywords, for instance, text analytics. A collection is any set of documents, and a document is an information entity that the user wants to retrieve. That doesn't mean that it has to be a complete article. It could be a paragraph of text. It could be even a sentence. It could be a photograph. So anything that sort of, it's a basic unit of retrieval, and it does not necessarily map one-to-one into, you know, the collection, say, of physical documents that were scanned and then OCR'd and then indexed. Index is a representation of this information. This is something that the search engine uses to find the relevant documents. And the word term is a word or a concept that appears in a document or in a query, and typically we match the query terms with the document terms, and that's how we perform the search. So as we said, documents are not just scanned, printed pieces of paper. This could be records, pages, so records in a database, for instance. It could be titles of movies or information about movies, okay? Another thing is that documents come with certain encoding. We usually assume that it's Unicode, but it could be ASCII. there is a lot of problem of moving from one encoding to another because the binary representations of letters changes. So therefore, I mean, there is a lot of software involved in converting document written in one format into a document written in other format. There is an issue of representation, that is how we represent documents. Typically, we would like a document to have a unique identifier, okay, because otherwise, how do we find it? But documents usually have some additional fields, so documents often have titles, and that's the format that we use, that a document has an identifier, a title, and it must have sort of a tag which says this is the body of the document. So in our case, this is the text tag. We already discussed document preprocessing, but basically the documents have to be prepared so that the search engine can actually perform the indexing correctly. So for instance, they have to be in a format that is acceptable to the search engine. I don't know, probably about 10 years ago, AOL released a collection of queries that people use on the web. So here we have, an excerpt from this collection, and what we see here is that this process of finding a relevant document is often interactive, okay, that people misspell, okay, people provide some additional information if they can't find it with the first query. People try alternative spellings. So for instance, here we have, Taj Mahal, and here we have Taj Mahal, but in one case it's spelled with a space. And then many queries that are not, would give you too many results. Do you love me like you say? That probably appears in many song lyrics. So even with some additional some additional constraints such as lyrics here, that might not be enough. So we have to add something about either the artist or some other additional information about these lyrics. But the point is that these sessions are interactive. They usually start with very short queries. There are typos. There is a small number of popular queries and a long tail of infrequent ones, but we still have to have a mechanism for dealing with them. And another thing that can be observed, that there is no advanced query operators, so Boolean operators like and, or not, or some additional operators like file type, PDF, or site ibm.com. People really don't use it. So the moral of this is that if we could provide an interface into which people could simply speak their query, there will be a lot of value because that would be both interactive. They would allow them to say something more than 2 words and then qualify the query if necessary. So what is the main concept that we should have some intuitions about when it comes to search engines? Well, the main concept is perhaps the inverted index. So we're going to sort of follow a Wikipedia example here because it's nice, short, and it sort of explains it relatively well. So if we have a collection of documents, so we have document 0, which says it is what it is, and document 1 says what is it, and document 2 says it is a banana. Okay, so these are very short documents. It's rare that documents are that short in any real life. But the point is that for illustration that will be sufficient. So what we find is that the word A, okay, appears in document number 2. All right, so essentially with what we do to create the inverted index, we list all the terms together with the location, the documents in which they appear. And so we have, banana appearing also in document number 2, but is appears in 3 documents, 0, 1, and 2. It appears also in 3 documents. What appears in 0 and 1. All right? So this allows us to essentially find out by performing a Boolean operation, if we want any combination of these words, we would find a document in which such a combination appears, or if there is, if it doesn't, then there would be no such document. So for example, if we have a query consisting of 3 words, what is it? Yes. What we would do is find, where what appears, which is in document 0 and 1, where is appears, which is document 0, 1, and 2, and the same thing for it. The intersection of these 3 sets is 0, 1. So from this inverted file index, we can quickly find the list of hits, which is sort of the list of document numbers, and then retrieve these documents to show either the whole document or a snippet of the document to the user. There is another concept which is full inverted index, and we need it if we want to do phrasal queries. Okay, so if we want to do a query consisting of 2 words which are next to each other, we have to know not only in which document a given term appears, but also in what position. All right, so banana to 3 means that it appears in doc 2, okay, which is the 3rd document. In the 3rd position, actually in the 4th position, we start counting with 0, okay. So this is the meaning of banana being into 3, all right. So with the same collection of documents, now a full inverted index looks like this. Okay, so we have a, we have a collection of pairs of numbers, but now we can perform more interesting queries. Namely, we can perform a phrasal search. So if we have a query, what is it? Yes, well, we can find first all the documents in which these 3 words appeared. This would be the same as before, but then we can check that in this case we have 3 consecutive numbers, okay, which means that they appear in consecutive position, and exactly in the position what, and then is, and then it. So this allows us to perform a phrasal query. So indices can be extended by providing additional parameters. Other extensions that are often encountered in practice is that we separately index titles, so we can perform a query. We want to find, say, influenza in the title of the document. I mentioned it before, but many search engines, including Google, allow you to include operators like and, or not. So you can perform queries like, banana and not it. We could also do it, or banana and it, or is and a. All right. I mean, all of these queries. I mean, we can do it in our little using our little inverted index, but this is something that is also very often used in practice, but maybe more by professionals than by sort of general public. The other concept, which is very important in information retrieval, is the concept of the vector model. So the idea here is that each document can be represented as a point in space, in the multidimensional space. So in this case, we have a three-dimensional space consisting of term 1, term 2, and term 3. And we have three documents. So for instance, document 3 has only term 3 and term 2, but doesn't have term 1. Document 1 has term 1 and term 3, and doesn't have a term 2. And document 2 has all three terms, because it's sort of, you know, it is a point in sort of which is not on any of these particular surfaces. Okay, so it is difficult to draw it in more than 3 dimensions, but the intuitions are exactly the same. That any mention of a word essentially, you know, creates a non-zero parameter on this particular term axis, and therefore, if documents have the same words, they would have the same vectors if we just care about the occurrence of the word. Okay? In practice, we look at some other stuff, not only about, you know, whether the word appears, but how many times appears. So if given word appears more than once, this vector may be longer. So that way we can also measure the similarity of two documents based on the frequency of appearance of certain terms. Okay, so here with our little example, we can see that this document would lie in this particular plane of the term it and of the term what, and what is it would lie somewhere in the middle of this space. Well, we can't draw the 4th dimension, so that's sort of somewhat impoverished representation, but this is the intuition that we need to carry with us. All right, so we have this document space, which is usually this vector space. So how do we match a query and a document? Well, basically, we treat the query as a vector, and we look for a document which is similar, okay, which is a vector which has a low distance to the vector of the query. And we can measure it in several different ways. So we can use Euclidean distance, we can do Manhattan distance, which is essentially looking at the difference on every particular axis. We can look at word overlap, but the two perhaps most frequently used, or at least in literature, measures as the cosine products, that is the angle between the vector of the document and the vector of the query, and this Jacquard coefficient, which is essentially measures how many terms are overlapping compared to the total number of terms in the query and in the document, which in practice means we care about the terms in the number of terms in the document. All right, so these are the basic concepts, okay? The concept of a document, query, and inverted index. Watson uses two search engines, of which one is the INRI search engine. And I'm going to show some information from a tutorial about in the search engine, just to give you an idea about the types of queries you can perform and sort of the language that can be used that goes beyond simple and, or, and not. So first of all, we discussed in previous lectures language modeling. Okay, so in this case, Lemur or INDRI not only sort of creates this inverted index, but also tries to measure, to create a language model of the collection. Okay, this is very useful in practice because what we found is that this model in which language model is taken into account when answering a query works better than just sort of the purely Boolean model of the query. So once this language model is built, what's happening next is that if a query is performed, that essentially we are trying to estimate the same way as we were sort of discussing language models in the context of machine translation, we are trying to estimate the probability that the query was generated by a particular document. So in other words, we try to match the query with the language model of the document. So what are the chances that the document would generate the query terms? This, gives us a nice quality search engine, okay? And this search engine also allows us to import different kinds of documents. So it comes with the capability to import HTML or XML documents, which is the format that we use. Or a variant of it is the TREC format, which is sort of contains XML tags of special kind, okay? But we can also import plain text, Microsoft Word, Microsoft PowerPoint. So despite the fact that this being sort of a experimental university-built system, the facilities for importing different types of documents are relatively well developed. In the query language, we can ask for a combination of terms, but we can also ask for a term, say, in a field, such as in a title. We can actually evaluate certain queries. We can ask about numerical values. We can also do some stuff with the results. We can specify how we want to combine the probabilities that comes from the language model, okay? We can do filters, for instance, by date, and we can also order the documents according to recency and express it explicitly in the query that we prefer more recent documents. I'm going to go through the next slides relatively fast. I just want to show that, again, the query language can be more complicated than just the Boolean query language. So, for instance, we can ask for a term or for a quoted term, like dog or quoted dog, but we also can ask about blue and car separated by not more than n words, say n being 2 or 3 or 5, or within a window. So here blue has to come before the car, but in this case it's unordered. The car can come before blue, so we are just interested about some neighborhood relation. We can provide synonym lists explicitly, and we can weight the synonym lists. So, for instance, we can, we care more about the car than about automobile. We prefer, twice as much documents that mention a car versus the documents that mention automobile. This weight is 0.5, this is 1. So there are more such facilities. So for instance, we can say that we want dog in the title, we want dog in the title or a header. We can do comparison, okay, so the year field should be less than 2000. The main query is this combine, okay, so this is essentially we would type, if we type dog and train, the implicit query would be combine, and that essentially says to the search engine, okay, give me you know, the most likely, the document that is most strongly associated with these two terms. There is negation, and there is a couple of other operators. We can do field retrieval, which was mentioned before. We can do passage retrieval, okay? So we can request that we want to find a passage which contains a query term, and we specify the length of the passage, and then, you know, how do we chop our initial documents with respect to, you know, created every 100 words. So there is some operation that's going to be performed to create the passages that we care about. And we use both sort of the normal type of search and the passage search. A few more of these. Okay, we can add weights on queries. To summarize, all right, what it is that we need to know to start discussing candidate generation and search in Watson? Well, we have to have some idea about an inverted index, so we covered that. We have to have some idea that, you know, how we connect queries and documents, and this is done by, for instance, using this vector model, and then the cosine is sort of measures the similarity of the query to the document. Not all queries have to be very simple, so I gave the example of a complex language which is used by INDRI to represent documents and to represent, you know, what it is that we want from the search engine. We know from experiments that this works better than the purely Boolean model. We have a very expressive query language. Now, I will not talk about it today. I might mention it again tomorrow, but essentially what we do in Watson, we use an abstract query language. So essentially we take the Jeopardy clue, we create a certain abstract object out of it, and from this abstract object we create different queries. So we create the INDRI query, which for instance might have some of these weights here, or might have a collection of other operators, or might include some synonyms. And we can create a Boolean query which would be passed to the Lucene search engine, which turns out to be that it works quite well for retrieving, you know, for instance, certain other kinds of information like parsed passages. So the point is that this translation from a Jeopardy clue or from some other query into a concrete query that's given to the search engine It doesn't have to be, you know, just a repetition, just copying, okay, just, you know, creating a collection of words and submitting it. It can be a process that uses our knowledge about, you know, what is the likely interpretation of the query that takes into account that some terms most likely form a named entity and therefore should be put together, but maybe we want these words within, say, a window of 1 or 2. So this idea is behind this translation mechanism from a simple collection of words with some additional syntactic information given from the parse to the concrete query in this very expressive language that INDRI allows us to do. All right, so to summarize today's lectures, we covered the process of question analysis. We discussed several methods of passage scoring, that is, finding a connection between the query and the evidence by looking at terms, by looking at predicates, by finding perfect matches, and by finding partial matches. We talked also about prismatic, about, you know, finding matches based on a pre-processed collection of text from which various relations have been extracted. Then we talked about data preparation, okay, taking text and then transforming it into a track format, creating new sources from existing text sources, and we talked also about corpus expansion to add the data that perhaps are missing with the existing sources. And finally, we covered some basic concepts of information retrieval, which will allow us later to talk about how search and candidate generation is performed in the Watson system.